Our sensor product is the microphone. The objective of this project was to calibrate a microphone that will be used to determine the distance between the sensor and a sound based on the amplitude. Physics of operation. Sounds are the result of pressure changes in a medium. In this case, it's air. Microphones measure these pressure changes. This particular microphone, a condenser microphone, uses a metal diaphragm as part of a capacitor. Changing capacitance when detecting pressure changes in medium creates an electrical output. The diagram on the left shows how this is done. Experimental setup. On the left, you see the microphone sensor and how it's connected to the power supply and DAC using circuitry. On the right, you see the sound source, which is an iPhone, and the known distance, which is a long meter stick. Static calibration. A sound at 698 Hz was played from the source, starting with 0 cm from the microphone. The amplitude was recorded after hitting the data collection button on the DAC. The distance was manually inputted and the decibel level was calculated. This value was verified using a decibel reader placed next to the microphone. These values can be seen in the last column in the table on the right. This process was repeated for increments of 10 centimeters, traveling from 0 to 90 centimeters and back to 0 centimeters. Here is an example of our static calibration. Move the sound source 10 centimeters forward, log the new distance from the microphone in LabVIEW, as well as the information displayed from the decibel meter and collect the data. Static results. On the left you see the raw data ranging from 0 to 90 centimeters and back. On the right we use only the first half going from 0 to 90 centimeters, and we include the least squares regression line, which has a static sensitivity of negative 0.1505 decibels per centimeter. Static design stage uncertainty. There are 5 different kinds of errors present in this experiment. Each of the 5 is shown in the bullet points below and has its own respective value. The total error, or uncertainty, was calculated using the final equation for a value of 2.1049. Dynamic calibration. A tone of 698 Hz was played once again at a constant volume. The sound was moved from 60 centimeters to 0 centimeters quickly, while the DAC recorded the amplitude over time. This allowed us to approximate the response as a step response. The data was shortened to 1 second around the time period with the changing amplitude. Then the data was condensed by collecting an average data point for every 10 milliseconds. A polynomial was then best fit to the condensed data. Time constant was calculated using a z-graph method, shown below in the bottom right, using points from the polynomial. This was repeated for 3 sets of raw data. Here is an example of our dynamic calibration. The dynamic results revealed that there were 3 overall taus and with an average of 0.1087 seconds. Summary and applications. The static sensitivity of the system was negative 0.1505 decibels per centimeter. The static design stage uncertainty was 2.1049 centimeters. The average time constant was 0.1087 seconds. Applications of this sensor include close-range applications such as security alarms and acoustic testing. On the left, you see the application for audio for security cameras, and on the right, you see the application for NVH and acoustic testing in automotive scenarios. Thank you.